moving really fast, and they're vibrating fast, that translates into a higher temperature. And then when the molecules start to slow down, that translates into a lower temperature. So really temperature measures thermal energy, which thermal energy is the motion or the vibration of the molecules. So at 100 degrees Celsius, the molecules are moving very fast. You got high thermal energy. Then at 0 degrees Celsius, the molecules are moving a little bit slower, so you have slower thermal energy. So and then we measure that thermal energy in degrees Celsius, Fahrenheit, and Kelvin. So we use those three interchangeable units. Heat, on the other hand, is the transfer or exchange of that thermal energy caused by temperature differences. So heat is a measurement of energy, and you can always identify heat because we see it in a word problem, because heat is going to have the units of either calorie, kilocalorie, or joules, or kilojoules. See, so that's heat. Heat's a form of energy because it has energy units. Temperature, on the other hand, is just a measurement of that thermal energy or molecular vibration, and it has the units of degrees Celsius, Fahrenheit, or Kelvin. So two totally different things there. So let's look at heat in action, or how heat is an exchange of energy. So when you put ice into water, see, the water gets cold. We know that from experience. But it doesn't get cold because the ice gives it coolness. Coolness is never transferred. It always works in the other way around. Only heat is transferred. And it moves like water does. See, like osmosis. Water goes from a level of high water concentration to low water concentration. Just like heat. Heat goes from an area of high heat to an area of low heat. So what's happening in the water, when you put the ice in there, what the ice is doing is that the ice is taking heat from the water because the water is warmer. So therefore, because the water had heat taken from it, then its molecules start to move slower, and then that translates into a lower temperature. Just like some people on a really hot day, they like to get some ice and then put it on their jugular to cool themselves down, but that ice is not giving you coolness. What that ice is doing is that it's taking heat from your body. And then the molecules that got the heat taken away from them are moving slower, so that translates into a lower temperature, so then you feel a little bit cooler. Not because the ice gave you coolness, but because the ice took heat away from you. So heat always goes from a level of high heat to an area of low heat. Coolness is never transferred. Just like water always goes down the hill, you never see water going back in the other direction. Alright, so that's our differences between heat and temperature. We're going to apply these in the next formula, and the way to identify them on paper, because they're all going to be word problems, is by the unit. So you can identify temperature by the unit of Celsius, Fahrenheit, or Kelvin, and you can identify heat by the unit. It's either going to be in calories, kilocalories, joules, or kilojoules. So let's take a look at the that formula, and that's going to be the heat capacity. So before we get into that, let's just look at one parameter of heat capacity, and it's this one right here. It's the specific heat. It's the C factor right there in the formula. And then here we have a table that lists some of the common specific heats, which is the C factor in that formula. And the heat capacities have these units. It has the units of joules per gram degree Celsius. So again, if you're looking at a word problem and want to know, okay, where is the specific heat in this problem with all these bunch of numbers? Well, it's the number that has this unit following it, the joules per gram degree Celsius. So there's a trend here that occurs. See, we're starting from a low value of specific heat to a high value of specific heat. So let's focus on that water. So water has high specific heat, and it's really good that it has that. See, we're about 65, 70% water in our bodies, and because water has such a high specific heat, it means that it needs to take a lot of energy before it goes up 1 degree, before it changes up by 1 degree. And it's that property that allows us to maintain, or helps in maintaining homeostasis. You know, because our bodies really have to absorb a lot of heat before our internal water temperature increases by 1 degree. And it's because of its high specific heat value. Now, let's go all the way up to where gold is. Gold and lead's about the same specific heat value. Those are the two lowest ones there. Now, whenever you have a low specific heat value, that means that the temperature changes are very drastic. So for low specific heat values, the temperature can change hot really fast or it could cool down very fast. See, so if we were made of gold, if gold ran through our bloodstream, that would be catastrophic. Because, you know, if we walk out into the sun, you'll heat up really quick. Then if you come into a room that's air conditioned, then you'll cool down really quick. And in our bodies, because proteins pretty much do a lot of the function in our bodies, they're temperature sensitive. You know, so high heat will kill them, low heat will slow them down. You know, so nature didn't choose gold to be in our bloodstream. So it chose water instead, because water, because of its physical property of having such a high specific heat, you know, you can go out into the sun and then your body temperature stays almost constant, your internal body temperature, because the water will have to absorb a lot of heat, that heat, in order for it to warm up. Or if you come into this air-conditioned room, you know, your body temperature will still be maintained. And even then your body